Okay, it's time to start learning about energy. And there's really two big important things you need to understand. First, that there are many types of energy. We're mostly going to be looking at mechanical energy or work energy, if you will, but there's all kinds of energy. There's nuclear energy, chemical energy, heat energy, sound energy. There's just all kinds of energy, okay? Secondly, you need to know that energy is conserved in a system. Now, why is that different or vital that you understand it? Because of this term in a system. Now, if we think about conservation rules, it just means you have to end with the amount you start with. But so many people say, wait a minute, why does it stop if my energy is conserved? Well, it stops because your energy is conserved in the Earth system, but not in your bouncy ball system or your Newton's cradle system or whatever other system, or your car system, right? That energy can transform to many different things, including things that escape into the air. It's still the same amount of energy, and it's still conserved because it's still on the Earth, but it is not in what you're particularly looking at, especially when we talk about mechanical energy with things. Now, as we're talking about mechanical energy, we're essentially going to be talking about work. And work energy is just a force applied over a distance. And so you often see it as work is equal to force times distance. Okay? But that's not the most common form that we think of. We usually think of things like kinetic and potential. And so you can often say that your work energy is equal to potential energy and kinetic energy. And they have their own different formulas, such as if I was looking at gravitational potential energy, by the way, because there are different types of even potential energy. That's simply going to be mass times acceleration due to gravity times the height. Well, if you look at this and you really break it down, you can see that this is a distance and this is the force of gravity. And so it is a force times a distance, right? And so that one's very easy to understand and see where it works into things. The one that ends up being a little bit more complicated for most people is kinetic energy, because its formula is 1/2 mass times velocity squared. And for the sake of things, I don't want you to think that I'm just making stuff up. So let's take a better look at it. Now, I have my kinetic energy formula, but I want to look at a couple of other things. For instance, I want to remember that my force is just a mass times an acceleration, and I even need to understand what that acceleration is, and so I need to understand that it's a final velocity minus an initial velocity divided by time, or the change in velocity over time, right? And so that is pretty much what we have for that. And remember, with work, it's a force being applied over a distance, so sometimes you'll even see it as a change in distance, right? That's what that delta stands for, is a change in distance. But to get how we get kinetic energy, we need to start with another formula, our old friend in kinematics. So if you remember from the kinematics unit, we had a final velocity squared is equal to an initial velocity squared plus 2 times the acceleration times a change in displacement or distance, meaning that I could rewrite this also as that initial velocity squared plus 2 times an acceleration times delta d. Ooh, well, look up here. We have that delta d in our work formula, and if we break down force a little bit more, you have that it's a mass times the acceleration times delta d. Ooh, well, if we have that there, we just need to solve for that in this kinematics formula and figure out what that's equal to. If we do, we're going to get that acceleration times the change in distance is equal to our final velocity squared minus our initial velocity squared divided by 2. Now here's another interesting thing though. We can always assume that we're going to be starting from a 0 point in velocity. If we do that, that's a 0 term, meaning we can rewrite this as a final velocity squared divided by 2, or 1/2 velocity squared. Well, look, that's our pretty much what we have in our kinetic energy formula, 1/2 velocity squared just being multiplied by a mass, and that comes from needing it to be a force. So if that is equal to acceleration times distance, and we multiply it by a mass, you now have a force being applied over a distance, just rewritten completely different for kinetic energy. So sure, you're asking, why do I need any of this? This seems kind of pointless and basic. Well, it's actually a very good and easy way to do a number of those kinematic problems before, because of the conservation of energy. Energy, remember, is not created or destroyed, it just changes form. That means that if I have, say, a projectile that I'm firing straight up, and I know how fast I'm starting with, I can really just figure out the kinetic energy of it, which is 1/2 times the mass times velocity squared. And so it would end up with 1/2 for this one times 10 kilograms times 5 meters per second squared. Now, I'll just go ahead and point out, don't forget your rules of operation. Please excuse my dear Aunt Sally, meaning I have to square this before I can multiply across. And so what's going to happen is I'm going to get 25, and then I'm going to go 1/2 times 10 times 25, and essentially I'm going to get, let's see, that would be 250, 125. 125 what? Joules. Because if I didn't mention it, that's your unit for energy, joules, shown by a capital J. Now, if I know that that's equal to that, but I want to figure out how high it goes, then I can think about the fact that it'll go somewhere up here. The mass will stay the same. It'll still be 10 kilograms. But when it gets to that highest point, it's going to have something new. It's not going to have kinetic energy. When it gets to its highest point, it's going to stop. But it's going to be off the Earth, so it's going to have a gravitational potential energy, which is just a mass times gravity times height. But we don't know that height, right? Luckily, we have a qualifying statement. Because of that conservation of energy, we know that the KE that it started with is equal to the GPE, or gravitational potential energy, that it'll end with. So now we know the gravitational potential energy, we know the mass, we know what acceleration due to gravity is, and we can solve it for that height. Meaning that all of that work we did with kinematics earlier for something going straight up could be done much easier with this. That is an H, by the way. And so let's see, we have 125 joules divided by a 10 kilogram mass. It's being multiplied by acceleration due to gravity. And we would get that it's a height of about 1.3 meters. Yay! Now, you said, well, if that's so much easier, why'd we go ahead and learn all of that kinematic stuff? And here's the reason why. Because it's much more difficult if you're talking about this going at an angle. You know why? Because notice I didn't have to worry about negatives. Since I didn't have to worry about negatives, that's because this velocity is squared, meaning you get rid of your direction. It's not going to have much of a direction. In fact, energy is a scalar, meaning it's a magnitude. It's not a vector. Energy simply is energy. It doesn't necessarily have a direction with it. There's aspects of this that have a direction, but energy itself does not. So if I'm talking about something at an angle, I have to be very careful when I'm looking at its conservation of energy, because it's just going to take all the sums of those parts. It's not going to worry about their vector components, because it's not a vector. It has energy. It's a scalar. And so it helps with some of those things. And if you're going straight up and down or side to side, you can do it pretty easily. But that doesn't mean you can do it as easily if it is a projectile at an angle. So how is it also useful? Well, you can calculate for a lot of different things.